So just to let you guys know, my name is Sarah Groff Hennigh-Palermo. That's a lot of names. I feel like if it's good enough for royalty, it's good enough for me. You can find me online usually as Sarah GP or Sarah GHP. I'm on Twitter, it's SuperSGP, so if you really like this talk, feel free to tweet about it. If you don't like this talk, please don't tweet about it. If you want to follow along with the slides, especially some of the code slides, it's at sarahghp.com/vBuffer. There's just a PDF there. And the code that I'm talking about and the examples that I have are also up on GitHub at WorstCat. That's a name of a very funny Tumblr that I stole for the repo for this project. So after the talk, if you want to see things on your own machine, feel free to head over there. So a little bit about me. I'm an engineer at Kickstarter. There's a whole bunch of Kickstarter people here too. Thanks for coming, guys. And in my spare time, I like to make digital art. And today, I feel like I'm here in both roles, as both an engineer and an artist. And this is the result of sort of a long adventure that I took from being a designer who kind of admired digital aesthetics and the way we could use art to interrogate things about code, to becoming somebody who's equipped both artistically and engineering-wise to answer those own kind of questions myself. And in some ways, that adventure started when I spoke here at Strange Loop 3 years ago about data art in JavaScript. I still have the same haircut, so some things I'm doing right. And I talked a little bit about why I thought the work that other people were doing was really amazing and vital. And then I went to the School for Poetic Computation, to the Recurse Center. I made a P5 library. I worked with the Office for Creative Research and got a master's degree, all sort of to get myself to doing the kind of work I really admired. And along the way, I've taken a number of self-directed accidental quests and journeys. And so today, I'm going to tell you about one of them. And this adventure took me through investigations into the kinds of differs that power things like Elm and React, through the basics of WebGL, through questions about performance, mostly in Chrome, and then through immutability, both in JavaScript libraries and in ClojureScript. And all of these were done in the pursuit of art and tools for art making. And I think this is really important for two reasons. The first is that when you're an artist, you're not always an expert. You're like trying to make this thing that you want with the tools that you have. And that can make a really interesting experience working with code. You know, you're not doing work for money. You're not doing stuff that has to work under some definition of like people come to your website and, you know, expect your form not to crash. And that really gives you a lot of freedom to do things counterintuitively and to find out new stuff. And it can be a really fun adventure. And so to reflect that spirit of adventure, today's talk is going to be in the form of an adventure story, where we'll follow our heroine, who bears an uncanny resemblance to me. I have no idea why. And she's going to meet some characters like the Differs, the keepers of the secrets to the VDOM, some helpful bush creatures. There's some friendly ghosts and witches along the way. And finally, she'll meet the garbage collectors and a wise old lady who pretty much will know everything at the end, in her quest to write fast and cool graphics programs using the latest in JavaScript tech. So now we're going to join in on our adventures in the vBuffer. All of the illustrations that are really cute are done by my friend Emily Griffin. She's Emily with Curls on Twitter. She's great. Working with her was great. I'm so excited to share fun slides with you guys. So please be sure to give her credit too. So anyway, as all adventures do, ours begins with a heroine who has knowledge but also discontent. She lives here in Webtown by the sea. She's a GLer, which is to say she's part of the group responsible for hardware-accelerated painting. And she has known since she was small, and you might know this too, that WebGL is an API for drawing on canvas elements. It uses the graphics card in the same way that games do to make hardware-accelerated drawings. It uses an API very similar to OpenGL, which is how non-web graphics programming happens. And these incantations can all be a little bit mysterious. I'm sure they look very mysterious. And our heroine knows that WebGL can be a bit peculiar, in particular because its parallel processing means lots of threads do lots of calculations all at once, but to keep them going, you have to talk to them in a particular way. And here at the beginning of our tale, the full workings of GL are still somewhat mysterious to our heroine. She does, however, have a vision of the standard look of GL work. It looks kind of like this, or maybe like this. Or sometimes it even looks like this. And while the math is amazing and hard, and the art can be really great, you know, it's just not our heroine's aesthetic. She wants to make things like these generative sand creatures, but maybe like 10,000 of them. Or something like these really cool forms that are made by Zach Lieberman, who is one of my teachers and is generally just always doing interesting stuff with 3D work. Or, you know, she might say, what would Ligia Pape's artwork look like if it was reinterpreted in GL Town? Or some Olga Rosanova, but like 10,000 and animated. You know, and she's been starting slow, messing around with things like some simple Brownian lines that interpolate their colors here, and some box collages. And it sometimes happens, you know, in any given village, a traditionalist will come by and be like, well, why don't you just build this in SVG if that's what you want? And, you know, she says, but certain things are really difficult to impossible with SVG, even though we don't always think of WebGL as being 2D. So the color interpolation on these Brownian lines is incredibly difficult to do in SVG, but relatively easy in WebGL. Or say something like adding all these weird pixelated textures to a bunch of cubes. Much, much easier to do using GL. So why not make something that she wants? Why not find a way to make something that's nice and fast, that does not have as many weird witchy incantations, that we can do without thinking about global state so much, and something where we can use a really cool declarative syntax like we have on the right, where instead of sort of managing buffers or the way the computer understands memory, we can just say, this is my data, now please draw it every X amount of times. So this is her goal, and this is what she wants to find, but these questions aren't going to be answered by staying here in WebGL Town, where everybody did things the same old ways. So instead, our heroine packs up her dreams in a bag in the night and heads out first thing to discover the best way to build the tool that she wanted. For in her country, it was not enough for ideas to come to one's mind. One must seek previous adventures and scraps of wisdom. And really, where is it different? And so she sets out. After traveling some time across the plain that abuts her home, our heroine first encounters a group that she has heard praised but never seen. And these are the differs. It's a sect that has made speed out of distinction, and she asks if they will help her. The differs multiply from 2 to 200 and begin to confer among themselves, chatting and trying to convince one another, sitting when they are unwilling to change their minds again, and finally resolving back into 2 with a stable decision, yes. And so they reveal to her the vDOM. This is a strange machine. It works much like the differs themselves had worked, taking in data, computing, and then reaching out and changing the world once they have their final answer. In its work, it seeks to answer this question. Given 2 versions of the DOM, what is the smallest change that can reflect the new truth? Because accessing and changing the DOM can be slower than comparing 2 JavaScript objects, a vDOM works by creating a virtual representation of each state in JavaScript. Then, when a set of changes comes down the pike, the differ finds the smallest change that can reflect that new truth. And usually the path looks something like this. We start off with an initial tree, changes happen, and a new tree is created with those changes. The trees are then compared, and a list of patches is generated from the comparison. The list of patches is applied to the DOM, and the initial tree is replaced with what was the new tree in this cycle, and it all starts over again. So let's talk a little bit about creating a tree. The data in the tree is usually an atomic representation of the system we're virtualizing. So in the case of the DOM, that would be something like an element node, in this case an H1. Element nodes can have children, et cetera. It's the DOM node you're probably most familiar with. Sometimes you can have something even more basic, like text, which is a node type, but it's much less complex, so it's nice to pull it out for itself. However, there's a third type of data that differs really like to leverage, and that's the thunk. And so this is a concept that's often used in 2 slightly different but interrelated ways, and at base, it's about delayed evaluation. And so sometimes delayed evaluation means a thunk is a function that knows how to diff itself. And other times a thunk is a function that's memoizable, which is to say that once evaluated, it does not need to be evaluated again unless the arguments change. In React, a thunk of the first type, a node that knows how to diff itself, is what you're creating when you write a custom should component update function. That's because otherwise React is testing whether things are the same just by checking their object reference. Are they literally the same object? And we'll look at this a little bit more in a second. A function of the second type, a memoizable function, is usually a pure function, which I know you guys are all at Strange Loop, so you know this, but it's to say it's a function whose output relies only on the arguments passed to it. And one of the best parts about this pure thunk is that you can just compare the arguments, which means you only have to compare smaller pieces. And so both approaches attack the central problem of diffing, which is to say when to re-render. Comparison is costly, and the only way to sort of completely know that the content of a data structure has changed is to iterate through all of that content. And so a data chunk that can tell you whether to re-render or one that allows you to compare smaller units are the keys to the differ's magic. Now, will this same magic work for our heroine, for WebGL? The differs do not know. They only know about the DOM. And so she must go on further to find out about how the GL incantations work. And so our heroine walks into the dark wood. Night comes, things get darker and darker and gothier, until finally she arrives at a clearing with a fork. Each path from here seems to delve into one connotation of what people mean when they talk about WebGL. To the left is the best worn path, and she can see through the trees, meshes, cameras, lights, scene graphs. There's even a really cozy looking A-frame off in the distance. This is GL as a way to create three-dimensional worlds and objects. And it's cozy, it's replete, it's full of libraries. This seems really nice, but it's not necessarily what we want. To the right, the path leads into a tight thicket, out of which sparks, lines, and really weird trig equations seem to come zooming. This must be the shaders. Our heroine has heard of these shaders, that they can make weird art very quickly. But apparently their magic is strange. The programs operate on each pixel very quickly, but only alone. They have no knowledge of the world, no history, no sense of the future. That seems maybe too weird. She'd probably end up like that three-eyed raven guy. Instead, ducking an errant equation, she heads forward where the path dips down and then appears to dead end into some boulders. It's dark and our heroine is tired. She lights a fire here by the boulders to cook up some hot dogs pilfered from the differs. Or I guess it just resolved itself back into one hot dog. Damn. Chomping away, our heroine notices there may be some drawings on the further rocks. She grabs her flashlight and heads out to explore. And there lie the basic secrets of the GL pipeline revealed finally. Behold. Graphics are made in the following way. The user starts by defining a set of triangles, which when combined together form more complex objects. This combination is called a mesh. Each triangle has 3 vertices, and each vertex has information attached to it. Its position, its color, text coordinates, etc. It can hold a number of arbitrary pieces of information at any given time. And then these are sent via the draw call to the vertex shader, which manipulates the described objects in a scene, eventually setting the vertices location via GL position, which is a special GL variable. Often this involves multiplying location values by a matrix uniform, which has been generated prior to the draw call. And this is the sort of matrices that you'll see if you're, like when you generate 3D perspective objects. From here, values pass through the fixed function, which is sometimes called a rasterizer or an assembler. And this changes the position values from theoretical spaces into pixels that are on your screen. If a type of variable called a varying variable has been provided to the shaders, this rasterizer also interpolates the values for that variable. So for instance, for a gradient, each vertex might have one color given to it, and then the varying variable will calculate all of the interim colors that you would get on your triangle. Now we have pixels. And these go to the fragment shader, which determines the final color of a pixel using its location in uniforms. And this is where those crazy partiers, when people are like, I coded up all these crazy shaders, man, this is sort of where they're doing their thing, is in the fragment shader. A lot of times they just draw like a flat rectangle and then lots of fun trick to make your crazy fractal shaders. And so in code, getting everything to the rendering pipeline before this happens looks kind of like this. You initialize the canvas and get a context, and then you set some global state flags. You got to make a program, and then you tell it about the shaders that you need. And then you get the locations for all your data, which you're going to need in a minute. You generate your data. You tell GL where to find your shaders. Oh, you set the attribute in uniform locations. Remember, we saved those like 3 steps ago? And then you send an element array to GL to tell it how to index into all the information you gave it. You compute your matrix. You set your matrix. You draw your element. And then if you want it to turn, you throw all of that into an animation call. And that's it. Right? That's like super easy. All you have to do to animate a single cube. It's great. And so looking at all these calls, one thing that may jump out at you that I want to address really quickly is that they're very procedural. And you're usually using a single WebGL object. So why not set everything directly on the object all at once, you might say? Well, because the GL context is used by a number of programs on your computer, there's sort of no guarantees about what context it's going to be indexing into at any given time. You could lose it, and then you're going to get a bunch of errors, so you mostly have to go through step by step to be sure that you are in your right context. So instead, we're here binding, sending data to the GPU, then rebinding, and making new calls when the data changes. So for instance, if you have position data, you bind that in, send it, bind your color, send it, and now you have new position data, you need to rebind it and resend it. And why is that? That's because inside WebGL is like the granddaddy of global state. And so anytime you're working with an array buffer, there's one array buffer that GL is working on at a time. And if you want to work on a different one, you have to be like, no, now we're talking about this other thing I told you about before. So it's a lot of code and a lot of state to keep straight. It occurs to our heroine that this whole VDOM thing might be adapted to vBuffers. Maybe that would be really cool. And so she sits down and begins to put things together. Hammering and sawing, typing and humming, she assembles her vBuffer renderer and a test example. The test example can render 2 types of cube geometries, a traditional cube and a sliced up one. And this is to test the effects of attribute buffer swapping. It animates the rotation on these cubes, creating a case for regenerating a matrix and then rebinding that matrix uniform each frame. So in WebGL, we create the object, and then the way you can appear to see it is based on our matrix. Excuse me. And it represents its data in objects for each type now. And so these contain the type of data that it is, its shader variable, and then as well as a name. So we can see that the positions use the same shader variable. It's always the position. But the names are useful inside our renderer. And then we have our data and our pointer. And the pointer is all the information GL needs to read the data that comes out. It's a float. Every vertex has 3 pieces with it, et cetera. And then the animation function just assembles these objects and mutations together and shoots them over to the renderer. The rendering function. This is the vBuffer differ, the core of the project, and this is how it works. So a component comes in, and if it's a draw call, we always run it through and call it. That's sort of how you measure when WebGL is going to call your next view. Otherwise, if it's new, we get and enable a location, and then go through to bind and set the buffer or uniform and save a new tree. If it's not new, the question becomes, well, has it changed? And if it hasn't, then yay, we're done. We don't have to do anything. If it has changed, then we go back to the binding and setting the buffer because we already have its location, and then it goes into the new tree. In this case, the differ uses the component name as the key for the vBuffer representation. And so if it doesn't exist, it instantiates the element, getting its location, and then going to bind and set, and saving that copy into the vBuffer for the next round. When the key does exist, the question becomes whether the data has changed. Fortunately, Lodash, which she packed away to bring with her, has a really nice equality check, is equal. So our heroine doesn't really have to think about what different means. Win-win. She begins to run the program. 1 cube, looks good. 10 cubes, still nice and smooth. 100 cubes, they're looking good. 1,000, you know. And then 3,000, oh, this one's 3,000. It's kind of slow, chugs. 1,000 was okay. They aren't spinning so fast. But why? This is a big problem. Our heroine can see into the art itself, but she doesn't really know what's going on underneath. How can she figure out what's wrong? She sits down to give a really good think to things and promptly falls asleep. No wonder, this adventure has taken days. And when she wakes again, it's twilight. Everything is still. The fragment fairies seem to have calmed down. Or maybe they just disappeared. Not everything is still after all. The bushes seem to be shaking. Our heroine definitely just saw some glowing eyes, or maybe a paw. A package comes sliding out from the bush creatures, wrapped in leaves and vines. And there's a coarsely scribbled note, "Hold this over your box." And so she does. Countdown appears, 4, 3, 2, 1, and it's replaced by this, a view into the box. Or maybe it's the performance tab on Chrome. And so the way this works is these red bits up at the top let us zero in on our slow frames. In this case, every frame is a slow frame. A slow frame is anything that runs under 20 frames per second, which is 60 milliseconds per frame. And a film runs at about 23 frames per second, just for context. And we can see which frames are the slow frames. So up at the top right there, there's that little red marker on them in the candle chart. And when you click on that, you can either scroll down and see the spots that are taking long because they have very wide run times, or we can look at the very bottom pane here, which lists the functions themselves. It's also possible to view a frames per second overlay while the function is running. This is a little bit hidden, but if you go into Chrome and type rendering into the command menu, a screen will come up and you can pick it. It's really helpful. And so in this other view, this is our view of all the functions now just sort of pulled up. Anything that has a very high self-time is a function that is itself slow. And in this case, it's a bunch of low-dash functions. Probably because deep comparison is expensive, but it's hard to know when it's inside a library, and you can't really change libraries, especially when you're trying to make art and not necessarily start opening PRs on open source projects. So the next step may be to see what happens if we go library free, which our heroine does. She strips all the low dash from her code, bangs a few things around, hits play, and nothing happens. She holds up the performance window, but nope, it has no insights this time. This stupid glade must be cursed, she decides. Noticing some steps cut out of the unmarked boulders, suspiciously absent till just now, our heroine climbs up and over the outcropping and marches away down the newly revealed path. She's sitting there, getting angrier and angrier, huffing and puffing, lost in her own mind about this bug about an hour later. In fact, she's so angry, she nearly bowls over a woman wearing a pointy hat and a t-shirt with "Witch Witch" written on the front. Who are you, our heroine demands. This is, of course, the reference witch. She can tell you which is which and what is what. She fosters static analyzers and enjoys making a bother of herself, which she proceeds to do until our heroine explains that the example is broken. The reference witch holds it, turning it slowly until the problem is revealed. You're never copying the object as you pass it through the differs reconciliation pipeline, she points out. Lodash must have been copying it for you before. That means as soon as you update it here, it's updated at the end. And if it's always compared to itself, new data is never sent to the buffer. You don't want to test if they're the same object, she laughs, only if the data has changed. The witch zaps the example a few times, causing the differ to emit updated objects when the data changes. These are then copied to the vBuffer. So now it goes, review the element. If it's new, create a copy using object.assign, make the binding and draw calls like we did before, and then update the old tree with new elements, copying those over again. This works to make sure that we are copying them all the way through, because if you have a reference, we're copying them recursively, because if you have a reference deep inside an object and you copy the object, the reference is still inside there in the same. And so this is quite a bit faster. 1,000 is smooth. 3,000 is still looking good. It's a little blocky. 5,000, I mean, this looks roughly like 1,000 did before with Lodash. And even 10,000, though chugging, is still moving. But since this is all of our code, what could be causing the problems now? What's the bottleneck we're hitting at 10,000? We grab our frame again, count down, 4, 3, 2, 1, and end up back in the summary tab. Here we notice that there's actually a link to the line of code that's been identified as being the problematic piece of code. So we can click through, and it turns out that now we can see the execution times for various lines of our code over there in the left. And one thing that's weird is the line that we were originally linked to down here, 219, that's not actually what's taking forever, but now that we're in here, we can take a look and we can find out that most of the execution time occurs when we're doing the mapping to generate the values for the new matrix. And that makes sense. You know, as the number of values in an array increases, you have to do more work. And she decides to check the reconciler. And here, a bunch of time is being spent in the main function that goes through each data piece. And that includes the attribute checks, which are taking a lot of time. This is one of the pieces we're changing every time, so it makes sense that it would take a lot of the time. And we can dig into which subfunction. So that's has not changed. That makes sense. And then deep inside has not changed, it becomes apparent that it is the content comparison that's taking a lot of time. That's what this array is. So the second most time arises every time we diff and check. But of course, that's all we have left once we've broken the line of references. We have to look at the actual values. The reference witch is familiar with the problem, but sadly, she cannot help. My magic is a bit limited, she sighs, but she has heard tell of an even stronger magic, adaptable but unchanging in those who guard its secrets. Up on the immutable immountable lie two castles, facing one another across a chasm. They are mostly similar, but slightly different. They don't care much for my kind up there on the immutable immountable, she says, and the climb can be grueling, but that's where you'll want to go. Our heroine, plucky, strong, and fortified by sandwiches from the reference witch, makes the climb. As she climbs around the two castles, she sees one is on her side of the road and the other is across the ravine, just as she was told. A broken bridge sticks halfway across. Our heroine knows where to start. Immutable.js is carved into the facade of the castle, which seems to be inhabited by friendly ghosts. There they are, waving from the windows. They welcome our heroine in and begin to explain that of course the keepers of immutability are ghosts. After all, they never change. They then begin to explain how to adapt the experiment. We don't use plain objects, they explain. We turn them into maps. And we don't use dot syntax, we use get and set. This JavaScript is strange and arcane, and our heroine has not seen these spells before. And so the friendly ghosts oblige. You see, immutability means that whenever you change the contents of a data structure, as we might with set, you're actually making a copy. You may keep the name the same, the identity, but instead of mutating the structure, you're just making a new copy. But because actually making new copies would take forever, we use a persistent data structure that uses structural sharing to make fast copies. Persistent data structures usually use a tree structure in which each node has some number of slots, often 2 for illustrative purposes, and each slot contains a pointer, repeated on down the tree until the final leaf contains the value. The slot at the very top gives us the length of the list. When something is added or changed, instead of copying the entire tree, a new pointer or set of pointers is added to reuse as much of the current structure as possible. Currently, these are mostly implemented using shallow trees that have 32 slots per node to keep insertion and lookup fast. Lookup itself is performed using bit partitioning, which uses digits as path keys and employs powers of 2, like 32 for instance, so that bit shifting optimizations can be used in lookup operations instead of needing to divide or use modulo. There's a really great write-up from Jean-Nicolas Lorange about all of this that's in a ton of detail. There's a link at the bottom here, and it'll be on the slides, my reference slides at the end. That's super worth reading. Probably don't even go to other sessions, just go back and read about persistent data structures. But with images of trees dancing in her head, our heroine is led up to a very nice room by the ghosts and put to bed. She wakes in the middle of the night to discover the ghosts across the ravine are calling her over. Our heroine creeps out of the castle. It turns out night is way less scary when the ghosts are very nice, and heads towards the bridge where the paren ghosts have gathered. They wave at her to cross. Hypnotized, she walks towards the center of the broken bridge. Each step lights up an opening paren along the handrail. Then, when she gets to the center where the walkway disappears, the closing parens all light up and the bridge completes. She continues across and is soon in the great room at Schloss Closure Script. The other ghosts explain that the previous castles stole their data structure idea, which is why they installed this magical bridge. Here, rather than adapting JavaScript, the code is entirely different, even though it's JavaScript that comes out at the end. So now here we can see how our data structures look in ClojureScript. The interesting thing with this approach is that instead of deciding where to enter into the world of immutable data step by step, as with immutable.js, data is always immutable by default, and instead, mutable structures can be explicitly chosen, for instance, using an atom. This means that instead of thinking about where it's faster to be mutable and immutable piece by piece, we're more often mindful of which actions are fast and which are slow. So for instance, the ghosts insist, use assoc, it's much faster than merge. They also note the reference versus values comparison appears here too, and this time the choice between using identical and equals. So for instance, the best babysitters and my fave babysitters are not identical, they're not the same data structure, but they are equal in the sense that they both contain Stacy and Claudia, clearly the best babysitters. We also get access to some weird cool closure spells, like hardcore destructuring, where you can have access to the inner contents as well as the object itself, which you can't do in JavaScript still. We can have some very elegant pipelining. That's what's going on with that little double arrow macro down there. You can pass your data through a pipeline the same way you might chain map calls in JavaScript. And there's some really nice built-in expressions, like if not, which is one of my personal favorites. And our heroine does find this code to be very pretty, but is it fast? She sits down and begins her work. She decides to leave functions that involve close interfacing with the GL API in plain JavaScript, and that way we can limit the interop to passing data structures through once they've been finalized. This limits the amount of time spent converting between data structures, which is a problem you're going to run into anytime you're using something that writes custom data structures on top of JavaScript. At some point, you're going to have to convert through to vanilla JavaScript, and being mindful of where you decide to do that can be very helpful. But how do these new Ghost versions work? Turns out the answer is not great, tragically. At 3,000, the immutable version is down to 9 or 10 frames per second, while vanilla is still at 26. ClojureScript, meanwhile, slips between 100 and 1,000. In fact, for this last one, our heroine had to turn on CPU throttling for the 100 objects view in order to see what was causing problems, because one of the interesting things is that when your performance tools use WebGL and you're trying to do WebGL performance, when you break everything, sometimes you don't have access to the tools anymore. So that's a case where the CPU throttling really comes in handy. And so this is not better, right? This is worse, but why? She looks deeply into the programs and notices that each time things get slow, minor garbage collection is high. It's pretty much will be the top function that's being called. The ghosts look sad and nod. The drawback with this type of immutability is that it produces so many extra data structures. The garbage collectors have to come by and clean them up. And in fact, our heroine begins to suspect that the immutable immountable is built on a big pile of garbage collected data structures. And so she had to go to the garbage collectors themselves. The ghosts float to a window on the opposite side of the room and point. And there, across a plain, at what must have been the very edge of the world, was a land shrouded in darkness, where buzzards and ravens wheeled. This is the land of the garbage collectors. Her heroine sets off to find the truth. When she finally reaches the border of the garbage mounds, she comes across this adorable but troll-like woman guarding the crossing. Here she is told that she can never return if she enters. Garbage collectors are unknowable. But the woman does offer her a slightly different art running box, explaining it has a new approach to running art, and it's called a safari. When our heroine runs her examples on this box, she finds that they are running slightly more smoothly, not dropping a frame or chugging where the Chrome example will stop. And that's because of Riptide, which is a new algorithm, the garbage collector explains. So all garbage collectors visit each object in memory and mark whether it's still in use or not. This can take a long time, relatively speaking, especially if you're making and discarding thousands of cubes frame by frame. In this newer version, the marking is done concurrently on a separate thread from that used as the browser. That means that the garbage collection won't block the browser's operation and cause slow frames. It's also done in parallel, meaning each pass can proceed more quickly. Riptide uses generational marking, which the garbage collectors note helps in particular with programs that allocate a lot. In our heroine's case, for instance, she's been using the spread operator with wild abandon. Our heroine is fascinated by the garbage collector's explanation, but she knows she has reached the end of her trail, and it's time to head home. This is not the end, though right now our heroine doesn't know it. Now she only knows she will return home without a good solution. No parades, no triumphal tales around the fire, no strangers buying her beer at the bar. It's very tragic. And a few weeks after her return, she is redeemed from her moping. An old witch, of whom she had taken little notice before, invites her in and asks her what did happen on her adventure. Sulking like it's her job, our heroine tells the witch, "All I learned was that I made a mistake." But being old and very wise, the witch is like, "Just tell me your story. It's okay if it's not a triumph. Mistakes are where all the best learning happens." And so our heroine recounts the story I've told you today, and together they find out what they really learned. To start small, we can say we've learned immutability's biggest limit is probably going to be when you're dealing with a lot of garbage collection, which, yes, I just rediscovered some of the problems with Lisp, but I did it really cute, so. Without careful attention or mutable escape hatches, using immutable data structures in a quickly changing program is going to create a lot of things to be disposed of immediately. And this might not matter if you're not doing animations, or a slow moment here or there is bearable. And so more broadly, we can say that she learned that not all clever adaptations are right for all problems. For instance, creating and diffing virtual trees is a great paradigm and can support some really great mental models, namely one where our view is a function of our data. But if you cannot prune the tree easily, diffing can quickly become slow. Meanwhile, mutation, which has been on the outs these days as everyone discovers how great FP is, which let us all agree, it's super great. Mutation, though, is really fast. It's probably what you need if you're updating 10,000 objects every frame. That not all clever adaptations are right for all problems is a key lesson, the witch notes, and one which we tend to have to relearn every time we find out about a paradigm we hadn't heard of before. Next, she found out that membranes matter, which is to say, she had the chance to apply different tools to the same problem, and in so doing, investigate their primary distinction, which is where each placed the line between reference and copy, the boundary where one piece of data became two, and the ramifications of these choices. The decision of where to place a membrane, what to expose through an API, what to ask your users to configure, which characteristic will determine downstream capabilities, these are at the core of the choices we make when we build or choose tools, which is to say, it matters where we decide to draw our lines. And so in the case of this adventure, vanilla JavaScript, because it mostly defaults to reference, allowed us to draw the membrane for copying in a small, tight place, where we create the virtual tree. It does have to be done recursively, as we noted, but it can still be in a very small single location. Immutable JS makes it possible to move the membrane wherever it works best for you. Though it mostly recommends the opposite, which is making things immutable where you're first creating the data, and then using internal escape hatches to make multiple mutable changes to a data structure. This is a very interesting approach. I think it's a little bit to the expense of syntax. And it does involve a lot of overhead, always considering how you're deciding to manipulate your data. Finally, ClojureScript has what I would say is an inverted membrane from vanilla JavaScript, where mutability can be declared at small points. And this is very interesting, but comes with a high cost of garbage collection. And that takes us to this lesson, which is to say that limits are inevitable. Whether the limit be reached at 1,000, 5,000, 100 objects, it exists. And if speed for 10,000 is what you need, the weird witchy incantations of WebGL are probably already optimized for you. But a really nice interface can exist for 100 and 1,000, and depending on what your art is, that might be enough. Oh yeah, so what was your art project anyways, asks the witch, other than the search? Here our heroine picks up the test example and shows the old woman. As they look at it, sort of sludgy, they notice that it has its own charms if you look at it just right. And though it wasn't intended to be the best art, just kind of a test for some limits, it turned out to be a little bit beautiful after all. And that's our final lesson. Failure is a really great medium. Z-fighting, which is what happens when your 3D objects and matrices don't line up right, is kind of beautiful. Glitch art is definitely a compelling aesthetic. And further afield, works like Slow Hot Computer by Sam Levine, which is about making your computer fail, is art and criticism of capitalism. It's a really great piece. There's glitch paintings. You know, not to mention every novel with an anti-hero. Failure can be really compelling too if we explore its limits and outlines. And meantime, what's next? Well, there's always these options. We can make an art tool with fewer than 100 objects. We can look into GPU optimizations and see the art of getting the most things on screen as possible, or head back to the fork and pick up that crazy fragment shader path. But for today, that's it. Everything in this talk is based on the work of intrepid adventurers who've preceded me. There's a whole bunch of link slides after this in the PDF, so you can go through and read through and keep the exploration up, and they can have their credit. And speaking of credit, I want to shout out Emily Griffin again, my illustrator. She did such a wonderful job, and so please check out everything online, and thanks so much.